All right, so we've already spent some time motivating this idea of a field of study called heat transfer, which focuses primarily on the physical phenomenon that if I take two objects that have different temperatures and I make them interact with each other, I put them in contact with each other, that over time the temperatures of those two objects are going to equilibrate. They're going to become the same. And you can imagine why this would be a particularly useful and interesting thing to study. And so we have to create this branch of science, so to speak, to allow us to be able to talk about this phenomenon in a way that is both objective and, at least as much as we can, precise. Like we want it to be precise. And the way that we start this process, the mechanism via which we're going to begin to do this, is by laying down the conceptual foundation of heat transfer through the relevant quantities that we care about in its study. All right? So we have to start defining what are the key things that we actually want to keep track of in heat transfer. When we start creating equations, what are those equations going to involve? All right? And the first thing and most important thing that those equations are going to involve is, perhaps unsurprisingly, the temperature. Now, once again, as we talked about in the previous video, we're not really too interested in defining precisely what temperature is. In fact, depending on what field of physics you study, you'll find that there are slightly different definitions for what temperature is. The only thing that we necessarily care about from the perspective of our study of it is that we know that temperature is a measure of how warm or cool an object is. All right? Whenever we say that something has a really high temperature, usually that means that the object is really hot. And so we are trying to track how that quantity changes over time. That's the goal of the study of heat transfer. But in order to be able to do so, in order for me to be able to communicate this in an objective way, I, of course, have to be able to construct some set of units, which are agreed upon socially as being the numbers that correlate to a specific, sensation of warmth or coolness, at least as measured by a sensitive and precise instrument, not necessarily something as clumsy as, our hands. And in order, again, to be able to do so, in order for me to be able to communicate information about the temperature of an object objectively, no pun intended, the idea is that we have to create units. And at least as of recording this video, there are three different kinds of units that we utilize for measuring temperature: degrees Fahrenheit, degrees Celsius, or degrees Kelvin. Technically speaking, most of the time when we refer to something as having a temperature of whatever Kelvin, we don't usually say the word degrees, but it doesn't really matter too much. And so the whole idea is that if I go up to my friend and I say, well, the temperature of this object is 98.6 degrees Fahrenheit, then they don't have to worry about whether or not I usually feel cold objects as warm or if something's going haywire in my brain, right? The measurement, the number 98.6 degrees Fahrenheit is supposed to be an objective physical quantity that I can communicate to other people and they will know exactly what it is. In the same way that I could say, 27 degrees Celsius or 300 degrees Kelvin or 300 Kelvin. And so, of course, the study of heat transfer is the idea of how these numbers, right, how those degrees will change over time. So we definitely want to try to understand how temperature changes over time. Usually we will refer to temperature with the variable T. It's a little bit of a no-brainer, but you can imagine if it ever shows up in any of my scribbles, you'll know that I'm referring to temperature. All right? Now, even though temperature is the base quantity that we use for the study of heat transfer, it is actually not necessarily the one that is the star of the show. In fact, notice that in the discussion, in all of this discussion that we've had about heat transfer, we've never even actually defined what heat is. And that's what we should do now. And so one thing that you should think about or consider is that model that I had talked about in my previous video about how temperature moves around between different things. And the model that had been created ages ago was that there was this invisible liquid called a caloric that would slosh around between different objects that were in contact with each other. And that if an object had a high temperature, it would have a large amount of caloric. If it had a low temperature, it would have a small amount of caloric. And that when these objects were together, it was basically like pouring a bunch of, invisible temperature water inside of a combined cup. And then it would eventually equilibrate the same way that, water eventually kind of has like a flat surface. Like no matter how you pour it, over time you'll eventually see that the height of the water inside of the cup is the same no matter where you are. So that was kind of the idea, that there was this invisible liquid that would slosh around and equilibrate in the same way that liquids under the influence of gravity usually do. And although you might think that this is kind of a very silly, outdated way of thinking about it, this is almost identically what we do today. There's only one small change to that idea. And the small change was based off of experiments where people realized, well, if I take a vat of really viscous liquid and I stir it super fast, okay? One of the things that you observe that starts to happen is that the temperature of the liquid starts to go up. Now that's very interesting, right? Because the temperature of the thing that I'm using is not necessarily, warm. So it's not that I have a warm object and a cool object and I'm putting them together. I'm taking two objects which are at the same temperature, and then I'm creating this motion, right? This stirring process that is somehow increasing the temperature of the liquid. And so a lot of people started to ask themselves, well, how could this be happening? And someone had an idea, and they said, well, we've been playing around with this notion of kinetic energy and gravitational potential energy, right? Like we love the idea of energy and whatever. So what if, whenever I'm stirring this liquid, the mechanical energy that I'm putting into the liquid via the process of stirring, what if some of that mechanical energy becomes internally converted into some other type of energy called thermal energy? And that thermal energy, that increase in thermal energy, correlates to an increase in temperature. And that is exactly what we believe. So rather than thinking of this idea of the caloric as being this invisible liquid, now we basically just say, oh, well, caloric is just a type of energy. Okay, caloric is just a type of energy that can flow between objects, but it can also be generated as a result of processes that convert one kind of energy into another. All right? And so just that quick edit, just that small little tiny correction, is what leads us to the understanding that we have of heat transfer today. And in particular, we call that thermal energy that is either generated or transferred in from other objects. We call that thermal energy heat. Now there's a couple of debates about what the proper use of heat is. Like sometimes we might refer to thermal energy as being just the property that the object has, and then maybe heat is that thermal energy in transit. But we don't necessarily have to worry about that too much because, again, context will bring it up for us. So we create this idea of heat and that this notion that it's transferred between objects, hence the name heat transfer. And because this quantity is now an energy, then we have to describe it using units of energy as well. And so in the international system, we would just say that heat has units of joules, right, which is the standard unit for energy. And so, okay, so now we're getting somewhere. We have this idea of heat, but we now have to try to figure out how this heat is transferred, right? The equations that we're going to create should involve the process via which this heat is transferred. In order to do that, we need to define a quantity that accommodates that notion, right? We have to create some notion of a heat transfer rate, which maybe is just, how much energy per unit time is being transferred from one object to another. And that quantity, unsurprisingly, like we were very direct when naming this, we just call it a heat transfer rate. And we usually refer to it with the letter Q. So you're going to be seeing a lot of Q's in here throughout the rest of the course. And this heat transfer rate, again, is supposed to be the rate at which this thermal energy is being transmitted from one object to the other. And so as a result, it has units of energy difference per time. And so in the international system has units of joules per second. All right? And so you might think, okay, this is enough. We have this thing that we call the heat transfer rate. And all we need to do is to try to create some equation that relates Q to T. And in many cases, this is in fact enough. We'll be able to get away with just creating some model that tells us what Q is as a function of t, and then we're all done. But it actually turns out that if we want to create like a properly rigorous, or at least try to create a properly rigorous physical theory of heat transfer, this Q is not enough. And it is not super obvious why it's not enough until you start seeing examples that kind of show what I mean. So let me show you what I mean. Let's suppose that I considered some sort of, I don't know, rock that is exposed to, I don't know, air, its surroundings, whatever you want to call it, atmosphere. And that this rock has maybe some temperature T1. And that the atmosphere, the surroundings, have some temperature T2. And we might ask ourselves, well, in this case, what is Q as a function of these two things? And this will work perfectly fine. We will be able to get away with this whenever the temperature of these two things are uniform. Whenever we can say, oh yeah, the temperature of this rock is actually T1 everywhere, and the temperature of the atmosphere is actually T2 everywhere. But what happens when maybe the temperature of this rock is not uniform? So what happens, okay, when maybe the top surface of the rock has one temperature and the bottom surface of the rock has another temperature? There it becomes a little bit more difficult, because now, even though we can certainly define kind of a net heat transfer rate from this rock to the environment, the physical process that governs how this occurs should be different, right? Because the difference in temperatures is different. Just to clarify what I mean by that, the difference between these two temperatures is not the same as the difference between this temperature and this temperature. And so you would expect that the physical process that is governing heat transfer is going to look different on the top side versus the bottom side of this rock. And if we want to account for that properly in our understanding of heat transfer, we can't just say, well, let's just define Q between two objects, right? And so what we do is we instead say, what if, instead of defining like a heat transfer rate for this object, what if we came up with this idea of a heat flux, which we are going to refer to with this symbol here, Q double prime. And how we're going to define heat flux is that we're going to say, well, maybe on the top surface, on a specific point of this top surface, maybe there's a little piece of this Q that's leaving the object, or coming in. We're going to assume that it's leaving just for consistency of arrow drawing. But we can imagine that there's a little chunk of heat that's leaving off the top surface. That little chunk of heat we're going to call Q double prime, or I guess more precisely, it's that little chunk of the heat transfer rate at the top. But then at the bottom, we're also going to have a little chunk of that heat transfer rate Q. And this is going to be true for every little point on the surface of the object, right? At the boundary between what we're calling the object, this rock, and its surroundings. And so everywhere along this surface, even on the sides too, we can assume that there is some tiny piece of this Q that we call heat flux. And we're going to define the heat flux such that if we take all of these little chunks, all of these little heat fluxes, and we integrate them over the boundary, that we get back the net heat transfer rate between the object and the environment. Okay? And so the whole idea is that rather than thinking about this heat transfer rate as just this one single thing that we define between objects, we can go further and define this thing called the heat flux, which is happening at every point on the boundary between an object and the environment, okay? And then we can always relate the heat transfer rate and the heat fluxes by integrating, adding up all of those tiny little heat fluxes off the surface, okay? And this quantity is what we are going to try to create physical models of, okay? This is resolution enough, so to speak. Now we have to ask ourselves, well, what units does this have? Well, think about it, right? You can kind of guess what those units have to be based off of this integral. If this has units of watts, like we saw before, joules per second, and this is an integral of something over an area, then Q double prime has to have units of this per area, right? So watts per meter squared in the international system, or heat transfer rate per unit area, all right? And so this Q double prime is what we're actually going to try to construct equations for, okay? And then if we want to find the heat transfer rate, we'll integrate, or in most cases just multiply by a surface area in order to get that heat transfer rate from the heat fluxes. Now, is this the end of the story? Not quite. There is one last thing, one last physical process that we want to consider in this study. And it stems from that little experiment that we were just talking about. The idea that if I stir, a viscous liquid, if I stir it fast enough, that eventually I'm going to observe that its thermal energy, and by extension its temperature, will increase, all right? And what you can imagine is happening there is that there is a process via which thermal energy is generated. Technically speaking, it's more like it's transferred, right? Because it's being converted from mechanical energy to thermal energy. But in general, we just describe this as being a process of thermal energy generation that occurs inside of the liquid, all right? And in the exact same kind of vein of logic that we talked about heat fluxes before, it's not really useful, or not necessarily super precise, to go into our discussions of how heat is generated, how thermal energy is generated inside of this cup, assuming that, we just define some like thermal energy generation, right? We define some rate of energy generation in watts, and then we just say, okay, well, that's the rate of energy generation. But that's not quite sufficient. What we want to do is to, like we did for heat fluxes, bring the resolution up a little bit. What we want to say is instead we want to say, well, at every little point inside of this liquid, there is a physical process that's occurring that's generating thermal energy out of all kinds of other energies that this liquid could have, okay? And that process can be described using and pardon me, I got to make sure that I write this correctly, a volumetric thermal energy generation, which I'm going to refer to using the variable Q dot, okay? And the idea is that at every little point, there's a little chunk of energy that's being generated. There's a little chunk of generation. And that if I take every point inside of this liquid and I add up all of the little contributions of the volumetric thermal energy generation, I get the amount of energy, or the rate at which I am generating energy inside of this system, okay? And so, again, this is basically a energy generation, so how much energy I'm creating per time, and then bringing it down to a point, so I'm dividing it by a volume. And so this quantity here has units of joules per second meter cubed, or just watts per meter cubed. And so, again, the whole idea is that if I were to define some kind of generated energy, like what is the rate at which I'm generating energy inside of the system, if I were to create a quantity like this, then I would describe it in terms of Q dot as the integral of q dot over the volume that I'm considering, over the volume of the object. All right, so just like we added resolution to the idea of the transference of heat between objects by breaking down the heat transfer rate into little chunks, we're doing the same thing where we're breaking down the thermal energy generation into volumetric pieces that we then integrate or add up over the whole object in order to observe what that thermal energy generation is. All right, what that net thermal energy generation is. And with these quantities, we have enough to be able to start talking about how we're actually going to relate this q dot and the q double prime associated with the heat flux to not just temperatures, but also the conditions of objects around them. And you're going to see that perhaps one of the most ad hoc and rickety, but also interesting features of the study of heat transfer is precisely how we connect heat fluxes and thermal energy generation, and even just thermal energy, how we connect these things to changes in temperature, which we will do in the next lecture.